Professor Nick Wright from MIT. Nick is a member of the Computer Science and AI Laboratory, so CSAIL at MIT. We all know him from his numerous contributions to planning under uncertainty, machine learning, and aerial robotics. So in particular, he founded the Project Wing project at Google X and led that from 2012 to 2014. And he's currently a director at MIT's Quest for Intelligence, which is a program focused on the science and engineering of intelligence. So very much looking forward to this talk. Nick, please take it away.
Thank you, Henny. Thank you, Soshi. It's a pleasure to be here. It's, of course, a challenge to say something new about curiosity following Pierre-Yves, who laid out, has laid out, over many years, a wonderful vision for how our robots should engage with the world and build their own models. And a lot of what I'm going to say today, I think, really follows in Pierre-Yves' footsteps, and tries to build off some of the work that he's done. And I want to emphasize that what I'm talking about today is that represents the collective work of many people, some of whom are here in the meeting today. So, several students and postdocs, and of course my colleagues, Leslie, Tomas, and Josh. And as Pierre-Yves very nicely laid out, curiosity really follows, people are curious, and children are curious. I actually think that, the colleagues and friends that we have whose curiosity persists into adulthood and maturity are some of the most interesting people. And curiosity really gives us a wonderful way to just engage with the world and learn more about the world. And also education theory tells us that curiosity is, an important part of getting people to actually learn the things that we need them to learn, that the best educators get people to be curious about the material. And what is curiosity? Well, a lot of the time when we think about what we want our robots to do, we're thinking about giving them goals, giving them specific tasks. And although we, obviously have goals embedded in our models of curiosity, it's really about being goal-free. It's about engaging the world in a way that doesn't necessarily depend on a specific task. And a lot of the time, we're synthesizing goals for sure, but they're not in pursuit of some external reward. And it leads us to do unexpected things like children climbing on countertops, etc. But it's really sort of engaging with the world to build a model. So why do we do this? Why be curious in the first place? An essential hypothesis, I think, of a lot of the work that we and others are doing is that it gives us, the curiosity is really algorithmic machinery that allows us to deal with the unexpected in the future by actually having a model of things that we don't necessarily need right now. We don't need models of what happens when we climb on countertops. We don't need models of every single tool that we're presented with right now. But our expectation is that in the future, we're going to have some understanding of how the world works. So we're going to have some understanding of things that we don't really need right now. So it's building a model of the world right now so that we can get the knowledge that helps the robot in the future. And hang on. Our approach, like many others, is going to be to have the robot build up a predictive theory of the world by learning from experience and from interaction with human teachers that elicits some phenomenon that we don't predict particularly well. And then we can gather more information that will allow us to improve our predictive theory. So the idea of curiosity is really, again, about interacting with the world now for the future. And one of the advantages of giving talks and going to workshops in the Zoom age is that one can ruthlessly steal from the previous presenter. And so this very much matches what Pierre-Yves said, and this was his slide from a few minutes ago, is that we really focused on building models of the world, and the name of the game is being able to actually think about what could be interesting about the world. How can we pick goals that lead to experiments that give us sensor data that allows us to improve our model? And so, again, very much following in Pierre-Yves' footsteps. And so what are the things that we need for a theory of curiosity? One is we need an idea for why we behave curiously, and we also need an idea for how to behave curiously. And we have some hypotheses for answering both of these questions, or sort of accomplishing both of these needs. The first hypothesis that I'm going to talk about is that why we do this is that it's going to lead to faster task execution in the future. And so I'm going to talk about some results that we have in demonstrating that curiosity does actually give an advantage in the future. But then, as Pierre-Yves talked for a bit about, is like, how do we actually choose the curious goals to actually improve our model? And Pierre-Yves gave some terrific examples about goal embeddings, et cetera. And one of the things that I'm going to talk about is that if part of why we're being curious is to do better at tasks in the future, then that's going to require us to plan for those tasks in the future. And can we actually use the plan structure in order to give guidance for how to explore the world? And then the last thing I'm going to talk about is how can we actually be very efficient about actually eliciting the compositional structure in order to explore the world. So those are the three hypotheses I'm going to talk about today. My stick is not working. All right. So let's imagine that the reason that we're exploring the world is that we want to be able to manipulate novel objects. Humans exhibit a wonderful ability to manipulate novel objects without prior experience on specific objects. For instance, if you walk into a kitchen, you can relatively easily figure out how to use the oven given previous experience with other ovens. And what is actually driving that? Well, certainly our understanding of how ovens work, expectation that there are knobs that turn the oven on, set the temperature, etc. We might even have an understanding of baking versus broiling, etc. But what are the cues that you're using in order to actually transfer that knowledge from one oven to another? And we very much believe that this transfer of knowledge is rooted in vision, is that you can very quickly perceive ovens. You can very quickly perceive doors and understand how they work. And we also know that a lot of the time, if the perceptual features of the objects that you're looking at are poorly aligned with previous experience, then that can lead to tremendous failures. How many of us have encountered a door that has a bar across the front of it that looks like it should push when in fact you're supposed to pull the bar, and that's very annoying. So how can we actually use the visual cues to enable this transfer of knowledge, and how can we explore the world in a curious manner that allows us to build this model of vision-based transfer from task to task, from door to door, from oven to oven. And so going back to our hypothesis is that we believe that when faced with a more complex task, if we've built models of the world through curiosity, that's going to allow us to perform future tasks faster than planning with a prior model. And so, why is this hypothesis reasonable? Maybe it's the case that curiosity isn't an extrinsic reward function that's learned from evolution, but actually we have a prior over tasks that allows us to, explore the world concretely. And so here's a very simple example of what we might want to do, which is imagine that our robot here, this is Baxter, is faced with some object in the world. It doesn't know what it is. It doesn't know it's a prismatic joint. And Baxter tries to elicit changes in the world. It tries to move the object around, and it can't, because the Baxter has some understanding perhaps of prismatic joints, but doesn't understand that the visual cues of the strong horizontal lines allow the robot to actually move the object back and forth. And so how might we encode a representation of the world that allows the Baxter to actually learn something useful here? Come on. Well, one thing that we can do is we can tell Baxter that we just want it to change the world. And so we can model a reward map using a Gaussian process that says, given a perceptual state of the world and given actions of its end effector, we can actually build a function, a Gaussian process, that actually predicts how much the world changes as a function of those actions. And if you know nothing about the world, then you're starting with a standard Gaussian process. Gaussian process allows you to actually correlate the actions and the observations you might have with one another. But if you have no information, then you have to assume that the prior of the Gaussian process, the mean of the Gaussian process is 0. And then over time, you learn to improve that representation. But that assumption that you know nothing about the world is, of course, wrong. you actually have previous experience with prismatic joints. You have previous experience with, again, doors and ovens. So how would you actually build that information in? You would actually build that information in this the mean of the distribution, the prior mean. And so where is that mean going to come from? Well, perhaps you can actually learn over time a mean of the Gaussian process that predicts the effects of your actions from images. So you have vision-based information from your robot. You have a function that allows you to predict the mean of the Gaussian process given the image and the action. And we're going to use a neural network because neural networks give us very effective ways of finding, making predictions of image-based information. And so given some novel context, some novel image, the Gaussian process can be initialized as follows. Given no immediate information, we don't know how this particular environment, this particular scenario is going to work, but we have some image information, and we can use that as a way to seed the prior of the Gaussian process. So train a neural network to predict the reward in terms of just the effect of the actions and images of the mechanisms. We can look inside the CNN to see that it's identifying key points of the images. And so the our neural network assumes the robot sequentially interacts with the different mechanisms for m steps each, and this allows us to predict which actions are likely to produce motion by associating visual features with the mechanisms. This, we have some prior information from previous interactions with previous objects, previous prismatic joints, and this allows us to make initial prediction. It's not going to be perfect, but what it does is it allows us, after seeing additional interactions with this particular mechanism, we can very quickly converge to the right answer. And so using simulated vision, we can give the Baxter some examples of different prismatic joints. And then 100 simulated sliders, Baxter is very, very quickly able to understand how this object actually changes. And you may recall the previous video where Baxter was not able to move the object very much, but you see here that very quickly Baxter's able to elicit large changes in the environment. It's able to move the object around very quickly. And then if we compare this to baselines such as UCB, we see that the system isn't learning very quickly at all. It has high variance in terms of the regret and in terms of the expected outcomes of the actions, but within a very small number of interactions with other objects, we're able to elicit large change. So and our first hypothesis is seems to be validated here, which is that when faced with new tasks, planning with models that we've learned through curiosity earlier allows us to accomplish tasks faster than something else that you might do. So good. Now, next hypothesis is, well, how should the agent choose the curious goal? So our first question was like, well, why are we curious? And it's in order to do better on future tasks. Now the next question is, well, how should we be curious? How should we choose curious goals? And and if we're actually going to be trying to accomplish tasks in the future, then we're going to be planning them. So maybe we should actually think about how our planning model, the compositional structure of a planning model informs our curiosity. Perhaps we should actually be choosing goals that actually produces compositional policies that roughly mimics our structure. And we know that this is important. I mean, Pierre-Yves talked quite a bit about this, and in terms of how do you actually pick the goals in an intelligent manner. And we know that random motor babbling has not been seen not to work. And we have an existence proof of how children learn. And so really that ordering of choosing goals really, and the curriculum with which our agents are curious seems to be tremendously important for building our models efficiently. And so the domain that I'm going to talk about here is block stacking. And the question is going to be like, can our agent explore the world of blocks in order to learn unexpected properties? One property that we're going to explore here is if the blocks have unusual centers of mass, that's going to really impact the robot's ability to do things like, block stack, build the tallest tower, build different kinds of towers. Then we've established that curious exploration really helps with future tasks. So how can the robot explore the world of blocks in order to do well? There's a bunch of things that the robot could actually be curious about. One is just like, can it actually build an understanding of things like the center of mass, maybe other properties such as friction if you're doing pushing, maybe other properties such as magnetism or adhesion. So the robot can be curious about just the observed state, or the partially observed state, the hidden state that the robot can't see. Another thing that the robot could be curious about is just like, what are the dynamics of the world such that it can achieve a goal. And another thing the robot could be curious about is how do the dynamics of the world interact with the partially observed state. And so we're going to assume that we're existing in a world where we have some state and we can take actions and we can accomplish some new state. And our future goal might be to build a tallest stable tower, but we don't know what those goals are right now. So let's think about construct. What do we want the robot to actually learn? So let's say that we want the robot to again accomplish tasks in the world. It's going to achieve. It wants to change the state of the world. And so let's restrict our dynamics model to predicting whether a tower is constructible or not. The dynamics model should be able to predict constructability for towers with arbitrary number of blocks. And so what do I mean by constructible? A tower that's both stable and that a single gripper robot can build by putting one block at a time. So that means that, if we have a tower that's constructible, all the sub towers under it also have to be constructible. And again, we're going to say that there's a latent property here that might be weird centers of mass that makes this a hard problem even for people to do. So this is stable and constructible right here because the centers of mass all line up nicely. This, just to make it clear that this is stable but not constructible. Why is this not constructible? So if I'm, this particular tower might be stable because the center of mass of this red block basically ensures that the yellow block's not going to fall over and the blue block's on the tabletop. But I can't build this, at least not with a single gripper arm, because when I put the yellow block on here, without the red block on top, the yellow block's going to fall off. And so I really want the robot to have some understanding of how the world works. So this particular problem depends strongly on an understanding of the compositional nature of how the blocks interact. And how am I actually going to get at that compositional structure? So we're going to represent the interaction between the blocks using a graph neural network. And so the name of the game is going to be, how do I learn efficiently my graph neural network structure that allows me to understand how the blocks interact in a way that allows me to understand how the centers of mass predict stability and constructability. And in particular, what I really need is an understanding of what do I know and what do I not know? How do I understand how good is my graph neural network at predicting right now how much I understand about the world in order to build these complicated towers? How are we going to represent the uncertainty? What we're going to do is we're going to use an ensemble of neural networks. And I'm not going to get too much into the details of how we actually use the ensemble of neural networks, partly because Mike Noseworthy, Izzy Brand, and Karis Moses have a poster later today. And so they're going to give a spotlight. I encourage you to go to the poster session and ask more detailed questions. But essentially, the ensemble of neural networks allows us to actually look at how well the different neural networks actually understand the dynamics of the world. And so our overall goal is to minimize the entropy of the neural networks. If the neural networks disagree in terms of predictions, then we're going to say that we're uncertain about a particular state of the world. One thing that we could do is identify when we're thinking about ways to explore the world, we could be thinking about future states of the world that minimize our uncertainty, that reduce the entropy of the predictions of the ensemble of neural networks. We're going to call that a greedy one-step approximation. The actual objective that we're going to use allows us to distinguish between two kinds of uncertainty. One kind of uncertainty might be because the world is fundamentally stochastic. We're going to call that aleatoric uncertainty. Like, we can't make accurate predictions because we genuinely don't know what's going to happen. We've put blocks, very close to the edge of stability, and they may or may not fall over. And what are you going to do? On the other hand, there's another kind of uncertainty that is reflected by the ensemble of neural networks disagreeing, but actually being very confident in their different predictions. And so what that suggests is there's information that's missing from different parts of the ensemble of neural networks. Our models are incomplete. We're going to call that epistemic uncertainty. And so what this different objective called the Bayesian active learning by disagreement allows us to do is to differentiate between overall uncertainty, which is going to be a combination of the stochasticity of the world and the incompleteness of the model, and the model entropy itself. So if we remove the uncertainty of individual components of the ensemble of neural networks, which is going to be a function of stochasticity, and we're still left with high uncertainty, that's going to be the epistemic uncertainty. And that tells us that we actually need more information about the world in this particular action, in this particular state. And again, I encourage you to go to Mike and Karis and Izzy's poster later today to learn more about this. And so the goal is, we're going to interact with the world. We're going to build different towers. We're going to synthesize particular configurations we might want to make, and we're going to pick the ones that are most informative in terms of reducing our uncertainty, in particular, reducing the disagreement between the ensemble of neural networks. And so experimentally, what we see is we're going to start by training on 10 blocks, and we're going to test on novel blocks that we've never seen before. And we can evaluate how well we do in terms of building 2-block towers. So we've interacted with the world, and now the task is just like, can we build towers? And if we're building 2-block towers, even random does well in terms of giving us some information about how the world works. But when we actually think about building more complicated structures, then we see that deliberate curiosity really, really helps. And what we see is that within about 200 interactions with the world, all of a sudden we're able to build 5-block towers. And by the time we've done 400 interactions, we're able to build 5-block towers with relative ease. And so we can also evaluate our interaction with the world in terms of just building structures. What does that allow us to do in terms of future tasks? Can we not just build the tallest tower, but can we build a tower with the maximum supported area? Can we build a tower with the largest overhang? And we see, again, very satisfying results is that on random versus the bald objective, the intentional curiosity, building the tallest tower, interacting with 3 blocks, doesn't make a whole lot of difference. We do a little bit better in terms of the largest overhang. But again, when we want to carry out much more complicated tasks, building 5-block towers that are tall or have maximum supported area, we're able, very quickly to do well. And these results are in simulation. Does this actually work in reality? Why are we trying to learn models of? Why are we trying to learn models that predict how tall towers we can build? Can't we just put the center of mass into some kind of physics engine and simulate forward? And the answer is yes, you can do that. But in fact, that doesn't allow us to take into account small errors in the manipulator, doesn't allow us to take into account unmodeled interactions between the blocks in terms of the surface properties, friction, etc. Actually learning the interaction between the blocks and learning predict how the blocks actually interact as you build taller towers gives us, relatively quickly, much better interaction with the physical world. And we see this on the real robot as well. So Mike, Karis, and Izzy, and also Sebastian put tremendous amount of time and effort into actually validating our theories in real robots. So this video here represents 55 hours of the robot actually carrying out interactions with the real world using our theory of curiosity. And the robot is able to build a model of the world. And then after 55 hours, we ask it to build the tower with the longest overhang. And it's able to do this very, very nicely. And so this is a wonderful validation of the hypothesis of curiosity. When we think about the limitations of this, are these, our hypotheses of does curiosity allow us to do well in a future task that it doesn't know about? The answer is yes. Does our idea of thinking about, actually planning interactions that give us maximum information gain? The answer seems to be yes, on the real robot as well. Limitations, we assuming full observability, we know the full parameterization of the state. We even know the specific state values. We just don't know the dynamics. And so future work that we're carrying out is, can we actually do this in a partially observable state? Can we learn the latent representation of the center of mass, for instance? And the answer seems to be yes, and we're pushing hard to get those results together as well. So last thing that I want to talk about, and I know that I don't have a whole lot of time left here, is we had a relatively simple representation and relatively simple task in terms of block stacking. So can we actually scale up to more complicated tasks? And our last hypothesis is that relational representations may give us an efficient way to explore even more efficient way to explore compositional structure. And the last thing I'm going to talk about is some work of Rohan and Tom, who've looked at relational model-based reinforcement learning as a way to explore the world even more efficiently. So again, we're going to think about goal-free in the sense that the agent is not given a specific reward function, and so the agent has to synthesize its own goals in order to actually explore the world. But it's going to be relational in the sense that states and actions are described using predicate logic, and this kind of reinforcement learning is going to be model-based. We're going to learn again an explicit transition model from the interactions. And the hypothesis that a relational representation is an efficient way to explore is reasonable because it allows us to do things like use lifting and symbolic transition models that, highly abstract representations that are, are much more efficient than low-level, highly physical or geometric representations. This is really about abstraction, and abstraction, gives us, tremendous computational efficiency in both planning and inference, and it's reasonable to believe it helps in curiosity. And so the specific difference to traditional RL is that RL is usually in a non-relational domain. There's no explicit problem setting or effect targeting. You're picking actions to take either according to your model or some mixture of models, and there's no typically planning or look ahead. And so here what we're doing is we're really planning to achieve goals, and the agent is pursuing specific or targeted effects it would like to see, as we saw in the previous work. What do I mean by relational? So we're going to have predicates such as the robot is holding objects, or objects are on tables, the hand is empty or not, and we have a set of objects. And so the current state is going to be a conjunction of literals, such as the robot is holding object A and B is on top of C and C is on the table, and so on. And we have actions that have effects, and then we may have specific goals that we want to take. We may have grounded goals that have specific literals included inside the predicates, or we may have lifted goals that have unbound variables in the predicates. And we'll see that these two different representations, these two different kinds of goals, have different effects. And so the transition models are written perhaps via lifted operators. And in this case, in a lifted domain, the operator has placeholders for objects. And of course, the actions have preconditions that must be true for the operator to apply, and effects that how the state changes if preconditions hold. And the algorithm in this case is to sample a conjunctive goal that has not yet been seen. And this relates very much to things that Pierre-Yves talked about. We have to set parameters in terms of the maximum number of literals that might be in there. And we also decide whether we're going to have lifted goals or grounded goals. And then we're going to plan to achieve those goals using our current understanding of the world. We're going to have operators that have preconditions and postconditions that may very well be wrong, but we'll try and achieve the goals using our current theory of the world. We'll execute that plan and use the resulting data to improve the operators and repeat. And what this allows us to do is to very quickly decide about or determine errors in the model. So we attempt to achieve a goal such as picking an object up. We've failed to do so because we weren't holding the object, and so we obviously need to add a precondition for the pick action. We test this in several domains, such as some of the classical planning domains, a simulated robot block stacking domain, and compare it to a number of state-of-the-art algorithms. And what we see is that this approach is extremely sample efficient in practice. Is that, in the black line here is the oracle ground truth, and what we see is the lifted inference in particular is able for some of these domains to very quickly achieve 0 error rate, which is what we want to see. And then we see planning success rate on new domains. We're able to, as in terms of number of interactions, we're able to get very quickly to 100% success rate as well. So we're seeing up to 2 orders of magnitude better sample efficiency than prior approaches. So the hypothesis is validated, and limitations are that there's these 2 competing approaches. One is a lifted domain, other is a fully grounded representation, and they perform differently depending on properties of the domain. And so, still to be worked out exactly how to know which representation to use. So just to conclude here, I think following in the work that Pierre-Yves laid out in the vision that we have here of curiosity as a way to actually build a better representation of the world that allows us to do well on tasks that we haven't encountered yet. I think the hypotheses are really bearing out that it allows us to get a good theory of how the world works. These strategies are going to be tightly coupled to the representation we choose, and the relational representations really drive the efficiency. Some work that Josh and his group, Josh Tenenbaum and his group, have done that I haven't had time to talk about here is that these relational representations also really seem to capture human behavior of exploration and curiosity. So we're not just seeing efficacy in getting the robots to carry out these tasks. We're also seeing that it's a good explanation for how humans explore the world. So again, I just want to acknowledge the work that Izzy and Sebastian and Mike and Karis have done for the block interaction work, and Rohan and Tom in terms of the relational work and the GLIB, and of course thanks to Honda, who've supported a lot of this research. So thanks again for the opportunity to talk about our work, and I'm happy to take any questions you might have.
Thank you so much. Thank you so much, Nick, for the great talk. That covered actually a lot of things, from vision to dynamics to relational reasoning. Maybe again, kind of, I'll start with a question, and then everyone else, if you have a question, please post it in the chat or kind of raise your hand. Maybe a quick question from my side. Let's start with the motor babbling, because in the beginning of the talk you said, well, motor babbling actually kind of doesn't work, and then at the end you used it, which I assume is kind of just a precursor to further research.
Yep.
So why did you use motor babbling in this case, and where do you actually see the challenges with motor babbling for the relational domain that you just described? Yeah,
so it's great, and I wouldn't describe the relational work, and I'm really speaking for Tom Silver and Rohan and Tomas Lozano Perez and Leslie Kelbling, and they may actually want to step in here and provide additional color to my answer. But I think it's important to distinguish like motor babbling, where you're just executing random motor commands as an attempt to learn about the world, from structured instantiation of a goal and then planning to achieve that goal. And I wouldn't characterize their work as motor babbling. I think the insight that if you use relational models to instantiate a goal and then deliberately plan to achieve that goal, that's not motor babbling, that's exploration. And I think if you, and Pierre-Yves talked about this very nicely, I think if you choose those goals, in a deliberate and informed way, you make progress very quickly in a way that motor babbling doesn't let you make progress. And I think the relation, and then there's a question of like, how do you actually structure your selection of goals? And I think the relational models give you a very nice way of structuring those. So I think it's motor babbling is essentially like, executing your limbs and seeing what happens, and that doesn't work. Whereas curiosity is about picking a thing to try and accomplish, planning to accomplish that, and then seeing what happens.
No, absolutely right. I like that explanation really well. It's kind of, in one case you're talking about the goals, and the other one you're actually immediately executing some random actions.
Yep.
So that's great. So if anyone has a question, kind of feel free again to raise your hand. But in the meantime, another quick question from my side. So in the learning of the dynamics part, kind of in the visual part at the beginning, you basically showed that when learning actually a higher tower, kind of a taller tower, then actually that's when curiosity really helps. Could you maybe elaborate a little bit on that, why that is?
Sorry, Henny, can you ask the question again? Like,
yeah, of course. So in the beginning, when you had the kind of the block stacking task, where the tower kind of needed to stay upright, you actually showed that if the tower is taller, then there is substantial benefit to kind of learning with curiosity. if you remember that part in the beginning.
Yes, that's right.
But kind of, do you have like a good motivation for that or reason for that? Why
Yes.
that is?
Well, so I think the short answer is that in order to build the more complicated towers, whether they're taller or have the longer overhang or a maximum supported area, like you actually need a better understanding of the world. And you know, it's not. I guess the short answer is that it's just harder to build taller towers or more complicated towers, and so you need a more accurate model. And so that's why curiosity helps. When you're building a 2-block tower or 3-block tower, you know, errors in your understanding of the world don't hurt you as much. And so, you know, a poorly constructed model based on, you know, poorly selected exploration of the world is still good enough.
Yeah, oh, perfect. There's another question here. How are you connecting perceptual information to the relational framework?
Good question. The short answer is that I think that we haven't done a great job of connecting perceptual information to any of sort of the later part of the talk, whether it's the relational framework or even just like understanding the interaction between objects in the world and understanding like latent variables like center of mass, et cetera. Completely agreed is that we haven't done that. I actually want to do that next. A question might be, how do you do that? And I think it actually gets to a problem of symbol grounding, is that I actually think that once you're learning about, you know, abstract operators, relational operators, et cetera, how do you actually connect those to perception? I think you have to do symbol grounding. I think you have to do perceptual abstraction. I have some ideas about that, but nothing concrete yet. It's a bit of a hand wavy answer. Sorry.
No, that makes absolute sense. I mean, symbol grounding is also kind of a rather kind of a complex problem that's been around for quite a long time, and I think that's not going to go away anytime soon.